Hello everyone. In this lesson we will focus on performance and capacity considerations while designing our machine learning system. So first of all, let's see why performance and capacity matters. So remember that our overall goal for designing any machine learning system is that we can improve some business metric. So we define some metrics which directly measures the effectiveness of our system, and the end goal is that metric should align with some business metric. For example, if we have some social media post, we like that more and more people engage with that, so there the goal is to improve the engagement rate. But this should not come at the cost of lower performance. It should meet all the system constraints, and that we will focus in this lesson. So there are performance as well as capacity considerations, and these are important during training time. For example, we would need an estimate of how much resource we need to build the model. For example, if it's a complex model and we have to train it with lots of training data, then we would need high GPU RAM, high RAM and storage requirements. And for a relatively simpler model, we would need less of that. So resource needed during building the model, and also during evaluation, how fast is that model, how much time it takes to process a query. So there are SLAs requirements that should be met. So this will also impact our architecture, because if SLA requirement is, let's say, so SLA means service level agreement. Requirements is that we have, let's say, 100 millisecond to give a response, and our model is too complex and it takes let's say 2 seconds, then it does not meet that requirement. So we will discuss more of that. So depending on SLA, we will for example, in this case, we will try to make our architecture simpler, so it directly impacts the architecture. So performance and capacity considerations, this governs the model complexity, like how much bandwidth we have, how much complex model we can get, and that in turn impacts our system architecture that we already discussed. Now there are multiple types of complexities that we must consider while designing our ML system. First is training complexity. It simply denotes the time to train a model, how much time it takes, whether it takes hours, days, weeks, or even months. Then is evaluation complexity, time to evaluate an input. And finally, sample complexity, that is amount of data needed for successful learning. And this is influenced by model capacity, because if you have a complex model, you will need lots of training data set. Generally, for deep learning models, which are very complex, you would need millions and millions of training examples, whereas some simpler models like decision tree based models will learn in relatively lesser amount of data, and even linear regression, those things will learn in even less number of data. So depending on, so it's influenced by model capacity or complexity. Generally, a complex model will have higher capacity, and that can learn more complex features. So it goes on, like we have some data, then we do training. So we estimate training complexity, how much time it takes to train, and then we evaluate it, how much time it takes to evaluate, and then based on the evaluation, we again collect more data, again train on more data, and this loop continues. So we have data here, we have training, and then evaluation. So these are the complexities. And if we talk about training and evaluation complexity, so this will help you in evaluating. These will help you in deciding your model architecture, like what kind of model you should use. So for example, let's say we have that SLA of 100 milliseconds. Then how would you estimate it? Why can I not use a deep learning model, or why should I go for a linear regression model? So you can estimate these, and depending on that, you can take your decisions. So you can do some asymptotic analysis. So let's say we have first, let's talk about let's say a linear regression model or any linear model. So if we have, let's say, features x1, x2, all the way up to, let's say, xn, or let's call f. So there are f features. So this model will do some linear combination of these things and plus minus some additional operations. So if we have n training samples and if we have f features, so this will be done for all the samples. So n times f times, let's say we run it for 10 epochs, or in general e epochs, then it should be some order of nf times e. So this is the training time complexity. You can take the asymptote. Similarly, let's say we have so during inference time this epoch will be 1, and data, let's say it's 1 sample, then it can be order of f. If we have n samples, we can have order of f times n. Similarly, if we have some deep learning model, so we have f features in first layer, input layer, then we have, let's say, I'm talking about some plain neural network, but even if it's not a plain neural network, you can replace that with features. For example, if you have some convolution layer, some convolution filter, let's say 3 cross 3, then you know that there are 9 features basically you are trying to learn. So you can replace that. But here, let's say we have f, then n1 nodes, then again in third layer we have n2 nodes, and so on. So we have, if again we have n samples, so n times f plus maybe f. So we will have all the nodes are connected. So you see f times n1 plus n1 times n2 and so on. So you get the idea. You can take some asymptote of that. And similarly, if we have a random forest, then you can think like what is the depth of maximum depth, how many trees are there in this multi-tree algorithm, so number of trees, and so on. So you get the idea. So this will help you in, make some estimation of how complex your model is and which model you should choose based on the SLA requirements. Now let's talk about an important aspect, that is scaling our ML systems. So we have to generally handle massive data sets and high query rates. For example, if there are millions of users and they are opening any social media page multiple times a day, so we will have some high query rates. Or even if we have a search engine, there are millions or maybe billions of users and they are making some average, let's say 5 to 10 searches per day. So let's say we have a high query rate, maybe 1000 queries per second, some general figure I'm taking, and we also have to train on massive data sets. So these will not be possible with a single system. So let's say we have some requirements. Let's say we have a performance requirement of 100 millisecond response time for 99% of the queries. So this is a typical service level agreement, and capacity is, let's say, 1000 QPS. And now let's say it takes, let's say we are searching something and there are, I search for a term, let's say flower in maybe Google search. So it's a very generic term and it's expected that there will be millions of documents that will match it. So let's say there are 100 million documents that match this query, but we have to filter out or do some processing, rank these documents and finally give it to the user. So if we do processing on these 100 million documents and one document takes let's say 1 millisecond or 1 microsecond. So if you multiply that, you will get 100 seconds. So it will take 100 seconds to process all 100 million documents, and it's a too long time. It cannot work that way. So what you can do, you can create multiple shards. So the solution is model sharding. So what you do, we have one aggregator. So you give it gets the input query and it distributes it, the load across multiple shards. So we create multiple model shards. So you can think of it as same model residing on multiple systems. So shard 1, shard 2 and all the way up to shard n. So in this case, let's say n is 1000. So this single system was taking 100 seconds. So if we distribute it to 1000 nodes, and then each node will return back the response. So you can think of it as 100 millisecond. From 100 second, we can do it in 100 millisecond. So now you see that this query is met, this requirement is met. So this is a way of distributing the load to multiple systems. In fact, it's exactly matching, but it should be further. So maybe n should be more than 1000 in this case. And it can, so I was talking about one query, but you can equally think like if we have 1000 queries, how much we should scale it further. So now let's talk about a very important concept called the funnel approach. It's also called layered approach because there are multiple layers or layered approach. So what happens is that let's say we use multiple models and we keep on increasing. So layered approach, that means there are multiple layers and there are multiple layers of models. So we don't take one very complex model and pass all the let's say we had 100 million documents, all the 100 million documents to this complex algorithm. So it will take lots of time. So what we do, typically we do some screening or some filtering, basic filtering, and initially we will have some simple model. So if you see this funnel, this size, the width of funnel is denoting the number of documents, the amount of data that we have to process. So here we have 100 million documents, which is a large number of documents. We have some simple approach here which does some basic filtering. Maybe it's a linear regression or some another linear model, and it filters out, let's say, from 100 million to 100k. Now the width of funnel has decreased. Here we can deploy somewhat, we can afford to deploy somewhat complex model, maybe 2-3 layers of deep learning model, neural networks, and then let's say it further filters out to 1k. And then we can have here a very complex, sophisticated algorithm, and we have just 1k documents. So we can use some complex model and it will efficiently rank those results. So ranking should be very accurate because users generally don't look at results beyond maybe 50, even 50 is a huge number. People don't go beyond that. So it's very important that the most important documents come at the top or maybe top 10. So this algorithm has to be very sophisticated and it cannot be done using linear models which are not that capable. So you see there are multiple layers, and you see why the term funnel is coming. So this is called funnel approach or layered approach. So we use multiple models with increasing complexity. In a stage 1 we have fast simple model and it narrows down candidates. It's like doing some basic screening. During interview we have thousands and thousands of candidates applying for a job, if you like to compare it with some real life example. So then some initial screening is very lightweight and we filter out, let's say, 100 candidates for that post, and then we interview them in depth. So it's something similar. And in subsequent stages, there is no rule that it should be 2-stage or 3-stage. But as we go further and further, we narrow down on candidates and we can employ more complex model. So the benefit is that it balances performance and capacity. So if we take a very simplistic model, it will be very fast, but the final result, that final ranking, may not be good. So I am referring to ranking. It's in terms of search result or maybe users posts on some social media. It can be some other use case also, like showing advertisements, which ads should be shown. So the last 5 ads that we are showing, that should be very accurate. So the later part should have more accuracy. So if we use simple model, performance is really good, but that I mean, you can have more QPS, but the performance, actual work that you have to do, that will be bad. But if you are using very sophisticated model, performance will be really good, but this QPS number will suffer. So you have to make a balance between these two. So finally, let's summarize. So ML system design involves in balancing effectiveness and efficiency. Then we should consider training complexity, evaluation complexity, and sample complexity, and we have to choose the models based on task requirements and resource constraints. So both are important. And then we should use distributed systems and the funnel approach to handle large scale problems. So see you in the next lesson. Thank you.